Welcome to Work, Energy and Power. You should be familiar with lots of different types of energy. Sound energy, light energy, electrical energy, nuclear energy, chemical energy, kinetic energy, gravitational potential energy. Lots of different types of energy, some of which have equations. We know that one type of energy, for example, gravitational potential energy, can turn into another, for example, kinetic energy. An object that's falling towards the ground will have a certain amount of gravitational potential energy based on its mass, the gravity of the planet that it's being dropped towards, and the height above the planet. We know that. The gravitational potential energy is at a maximum just before it falls. As it falls, that gravitational potential energy turns into kinetic, and all of it has turned into kinetic energy the moment before it hits the ground. So the kinetic energy is a maximum down here. And we say that the gravitational potential energy at its maximum is equal to the kinetic energy at its maximum, which allows us to equate these terms and then do some calculation. Maybe we have a missing value. We know that energy can turn from one type into another. The amount of energy that has been changed from one type into another is known as work. The ability to do work, the ability to change energy from one type into another, is an incredibly useful thing. The amount of work that has been changed is also given by this equation. And there is always a force pushing an object through a distance to allow energy to be transformed. In this example, we have our mass, we have our object, and it's being pushed towards the Earth by the force caused by gravity. The distance that it's travelled is the distance that it has fallen. And the work that has happened is the gravitational potential energy changing into kinetic energy. So the force due to gravity, mg, and the distance that it's travelled, the height that it was dropped from, is equal to the gravitational potential energy that it had. And we know that the amount of work that's been done is equal to this because we know that all of the gravitational potential energy was transformed into kinetic energy. If the direction of the force and the direction of the distance moved do not agree with each other, then we need to do a couple more calculations. Here's a good example. A box being pulled along the floor for a distance, but it's being pulled by a rope applying a force at an angle to that direction. So what we have to do is essentially resolve the force in that direction. As long as the calculation for work is done where the force and the distance are in the same direction as each other, we will come out with a correct answer. We could resolve distance for the direction of force, or we could resolve force for the direction of the distance moved. Either will work. In this situation, when we resolve it, we get F cos theta. And so the work done will be equal to F cos theta multiplied by the distance. You may sometimes see this as written, the displacement multiplied by F cos theta, but it's the same equation. Power is the rate at which work is done. And whenever we have the word rate, what we really mean is per second. So power is the rate at which work is done. And remember that work being done means that energy is being transferred. So it's the rate at which energy is being transferred from one type into another. And power is equal to the amount of work that was transferred divided by the time it took for that to happen, otherwise known as work per unit time. There are many other ways to calculate power, for example in electrical circuits, but this is the definition. If we substitute in some of the previous equations, then we can analyse and get a couple more equations. We know that work is force times by distance. And if we have a look here, we can see that a distance divided by a time, that's a velocity. So it can also be force multiplied by velocity. Another thing we can do is we can draw a graph of force against displacement. Remember that displacement can also be thought of as distance. If we have a very, very simple graph, then the area beneath it is going to be the product of whatever is on the axes. So force times by displacement, that means that the area beneath the graph is going to be the work done. If we have a more complicated shape, like a triangle, then we just use the rules of geometry to work out the area of the triangle. Another shape that you may come across is something called a hysteresis loop. If you load a stretchy material and you observe that it changes its length, then you may get a shape that looks like this. If you then measure what happens to its length as you remove the load, you may get this type of behaviour. Indicating that it has permanently deformed, it's permanently changed its length, it is stretched from the starting conditions to this value. And there is also a difference in the area beneath the graphs. The area beneath the loading graph is this, and the area beneath the unloading graph is this. What this information tells us is that the energy used to stretch the material is greater than the energy that you got back when the material relaxed. And the difference went into heating and deforming that material. Efficiency is the proportion of the original energy that did what was intended. It's calculated by dividing the useful output by the total input. So what you get is a number between 0 and 1. If the useful output is exactly the same as what you put in, then you get a value of 1. But if the useful output is less than what you put in, you get a number less than 1. If you multiply your answer by 100, then what you're getting is a percentage between 0 and 100%. So if you have 100% efficiency, then everything that you put in becomes useful output. And if you have 0% efficiency, then nothing of what you put in becomes a useful output. Sometimes you'll see a symbol given for efficiency, and that is the Greek letter eta. It is a lowercase letter, but you won't often see it in A-level textbooks.